So hopefully today is going to be one more interesting lecture. And I think you need to pay attention because you wouldn't be able to find this kind of material presented in this manner in any resource. I haven't come across such a resource so far. So you have to be attentive in class. Today we're going to kind of wrap up our discussion on magnetoresonance. So basically today is our second lecture on magnetic resonance. And now we've entered the practical realm. We're trying to look at practical implementations of quantum circuits, quantum networks, quantum information processors, quantum sensing devices, and etc. So we're trying to give a more practical flavor to our course at the moment. So can you remind me what the time-dependent Schrodinger equation looks like? Iota h bar, the derivative of the quantum state, which now is a function of time, equals the Hamiltonian acting on the quantum state. So when we solve this equation, solving this equation means finding the time course of the quantum state The time course of the quantum state means you look at the quantum state at some time 0, and upon this initial quantum state acts an operator. That operator is e raised to power minus iota h, the Hamiltonian, t over h bar. All right. So this is the time dependent Schrodinger equation, and this part is the solution. Now, if you want to see how a quantum state changes with time, we need to find out the Hamiltonian. And we are looking at one specific problem. That specific problem is a proton inside a magnetic field. The proton is a spin, it's a tiny magnet, and its energy changes when it's placed inside a magnetic field due to the Zeeman effect. And we were able to write down the following Hamiltonian for a proton inside a magnetic field when the magnetic field was pointing in the z direction. And that Hamiltonian turned out to be h bar omega over 2 the z operator, the poly z operator. So this is the Hamiltonian for a spin inside a magnetic field pointing along the z direction. So a spin such as a proton inside a z pointing field. Got it? Now the thing is that I just want to remind you of what these Pauli operators are. The Pauli operator z is given as 1 0 0 minus 1, x is given as 0 1 1 0, and y is given as 0 minus iota iota 0. So these are the cardinal Pauli operators. If the magnetic field were along the x direction, we put an x here. If the magnetic field were along the y direction, we put a y here. And we also proved a theorem in the last lecture, and that theorem was as follows: e raised to power I theta a, where a theta is some real number, a is a matrix, an operator whose square is identity. It's an idempotent matrix. This expression, the exponent of a matrix, such a matrix becomes cosine theta into identity plus iota sine theta into the matrix itself. And we proved this. So if there were a minus sign here, a minus sign would appear here. So this is a theorem that we all need to prove. It's going to be given as a homework problem and so on. And we know that these matrices, the 3 Pauli matrices, are idempotent. Each one of them is idempotent. So this could be an X matrix, this could be a Y matrix, this could be a Z matrix. So far so good. Now suppose we look at a proton inside a magnetic field. This is the Hamiltonian. So the proton is placed inside a Z pointing magnetic field. And we suppose that the initial quantum state for the proton is ket 0. Now what does ket 0 mean? If you look at a proton inside a magnetic field, it's going to have 2 quantum states. The physical degree of freedom that we're looking at is the spin of the proton. The spin could point parallel to the field, it could be anti-parallel to the field. So if this were my direction of the magnetic field, some B, it's pointing along the Z direction. If the spin were pointing up, this is my spin, this means the magnetic moment points up, I call this ket 0, right? I can do that. Just now we're not talking about the photon polarization or the path of a photon, we're talking about the spin of a proton. So spin parallel to the magnetic field, ket spin pointing up is ket 0, and spin pointing down, let's call this ket 1. So now the physical reality that we're looking at is the proton spin, and we're using the same quantum language that we've become so familiar with by now. So this is the scenario. So our initial quantum state is the spin pointing parallel to the magnetic field. This magnetic field is along Z and the spin also points along Z. Now time keeps on clicking. Time is a parameter, time changes. Now how does a state evolve with time? The time dependent Schrodinger equation is an equation of motion. It tells us how does the state change with time. So if this were my initial quantum state, I would just need to put in the initial quantum state here, and the operator, the big operator in which the Hamiltonian sits on in an exponent position is applied, and I can tell what the state is going to look like with time. So first of all, let's calculate this operator. Okay, I know what the Hamiltonian is, I can calculate the operator. The operator of course is going to be a unitary operator. So let's call this operator U. This is E minus iota h t over h bar. So e raised to power minus iota h, the Hamiltonian is given by h bar omega over 2 h bar t z. All right, this omega, by the way, this omega, this one, this omega is given by minus gamma b. So it's proportional to the magnetic field. Higher the magnetic field, higher will be this frequency. Omega has dimensions of frequency, and this is a constant of proportionality. We've derived this in the previous class. So if you look at this expression here, the h bar goes away, and I'm left with my u becomes E minus I omega t over 2 z. Now what I would like to do, I would like to use a theorem here. So I keep all the constants separately and just look at the matrix whose square is identity. Z is such a matrix. So I just apply the theorem that we've seen so far. So what would the theorem give me? What is this exponent equal to? Cosine of omega t by 2, identity, don't forget the identity, it's an operator, minus I sine omega t over 2 z operator. So this is my unitary operator. This acts on the quantum state. Now what I could do, I could write this in matrix form. Since I'm dealing with a single qubit, the spin half system is a single qubit, it's just going to be a 2 by 2 matrix. So could you please for me write down the unitary operator corresponding to this Hamiltonian? It's going to be 2 by 2 matrix. So what does the matrix look like? Cosine omega t by 2 minus iota sine omega t by 2 and a 0 here, right? 0 here and a cosine omega t by 2 plus iota sine omega t by 2. So this is my matrix, correct? And I can write this in a slightly more compact form as E I minus I 0 0. So this is my operator. This operator acts on the initial quantum state. Now the initial quantum state is given by ket 0. So my state after some time is going to be this operator acting on ket 0. So what's the result of this computation? What is my output quantum state? So correct? This is my quantum state. Is this quantum state simply ket 0? Is it ket 1? Is it ket 1? No. Is it proportional to ket 0? Yes. I think it is ket 0 because this factor here is a global phase. This is with everything. This is not inside the vector. This has been factored out. So it plays no role when you calculate the probabilities. Because when you calculate the probabilities, you take the modulus square, and this is a pure phase factor. It just factors out. It just gives rise to 1. It's complex. Its modulus is 1. So this really is E minus omega t over 2 ket 0. This is a global phase, it's immaterial, it doesn't play any role in the physics in most cases. Anything that is inside here, any phase factor that is inside here will play an important role, but this doesn't. So is the state changing with time? So what is the change? Right, but I've mentioned that this does not have any impact on any results.
So then it doesn't change.
It doesn't change. The quantum state just stays where it is. Sorry? It's a time independent state. If you kind of learn linear algebra, you would notice that this quantum state is an eigenstate of this matrix. Yes, please.
Sir, I'm a little confused. Could you please explain how we used a time dependent equation and ended up with an equation that is not time dependent?
So we start off with a time dependent equation. This is our time dependent equation. This is the solution. So the quantum state is this. Supposedly it changes with time. The problem is that the time dependence is only in a global phase factor, which is immaterial. It's possible that a state does not change with time. You can still have a time dependent equation and a state that just remains constant. So the state is a constant of motion kind of thing here. It's possible. So global phases do not matter. Any phase that comes with the entire ket does not matter. We've seen this in some homework problems as well. Global phase, that is. Now, if you start off with the quantum state ket 0, nothing changes. But suppose my initial quantum state now changes. I use a different initial quantum state. Now my initial quantum state is 1 over under root 2 ket 0 plus ket 1. So the same Hamiltonian, the same physical system, proton inside a magnetic field. The only difference is that my initial quantum state is now ket 0 plus ket 1. Could you find out whether the state changes with time and what is the new time dependent quantum state? So my initial quantum state has changed. The propagator, the unitary operator remains the same as it originally were. Right? Got it? So let's do the matrix multiplication. My initial quantum state has changed. It's the same proton now initialized in a different initial state, in a superposition state. Let's see what happens. So 1 over under root 2 E minus I omega t over 2 and E plus I omega t over 2. Now let's kind of factorize out a phase factor and write this in a neater form. I would like to write this in a ket form. So you can go from ket to matrices, you can go back from matrices to kets. So now I have this quantum state in vector form. I would like to write a ket out of it. So how I would like to do this, I would just, first of all, I would like to factor out this factor and treat this as a global phase. Just bring it out of the vector. Everything else remains. I get 1 here. What do I get here? Sorry. E I omega t. Correct? Now this means my quantum state as a function of time is 1 over under root 2 ket 0 plus E I omega t ket 1. Now is this quantum state changing with time? It is. It's evolving with time. The quantum state at time equals 0 is going to be the superposition state ket 0 plus ket 1. With time it's going to change. For example, if I were to take this state at time equals 0, what is this state equal to? I can just ignore the global phase. I mean, this is immaterial. It doesn't matter. It's a global phase. So I can write it if I wish to, but it's a global phase and can be ignored. I'll take questions. Just let me finish my argument. What's the quantum state at time t equals 0? If I put t equals 0 here, what do I get? What do I get? 0 plus 1. This indeed is my initial state. If my omega t were, say, pi by 2, if my omega t were pi by 2, then this would become 1 over under root 2 ket 0 plus iota ket 1. Got it? If my omega t were pi, this would be ket 0 minus ket 1. If it were 3 pi by 2, this would be ket 0 minus iota ket 1. So this kind of constant evolution of the quantum state between a variety of quantum states. I can show this in graphical format. I'm going to do that in a minute. But let me first take some questions. Yes, please. ये वाली क्योंकि यहाँ पे ई आई ओमेगा टी बाई 2 था ना, तो जब इसको मैं इससे मल्टीप्लाई करूँगा तो यही आ जाएगा. ओमेगा स्क्वायर कैसे होगा? ठीक है. There was one more question here. Right. Any more questions? Yes, please. This is a number, a complex number. I can write this as correct. आप इधर देखें ना जहाँ आपने सवाल पूछा है. Is this correct? So if I have something of this kind, I can write this as I theta into E minus I theta by 2, etc. Alright? Now let's look at this quantum state. I want to depict this evolution of a quantum state, of the quantum state graphically, so that things become easier to understand. And the picture which I would like to use is the Bloch sphere. So let me explain the Bloch sphere and putting it all together. By omega t, rotation by omega t. I draw a sphere. Now this sphere is a hypothetical sphere. It's a mathematical object or geometrical object. It's not a real sphere, but we say that all the quantum states for the qubit, only two level quantum systems, only qubits live on the surface of this sphere. This sphere is called a Bloch sphere. Now, on the surface of this sphere, we need to identify different cardinal points. What we're dealing with here is a magnetic field pointing along the z direction. This has two basis states, and they're orthogonal, ket 0 and ket 1. So they must be on opposite sides of the Bloch sphere. Any two orthogonal states are on the opposite points of the Bloch sphere. So if inside this Bloch sphere you were to draw a diameter, the opposite points on the sphere will represent orthogonal states. Two cardinally opposite points, diametrically opposite points, will represent orthogonal quantum states. So conventionally, on the north pole you have ket 0. Ket 0 lives on the north pole of the Bloch sphere, very top. So the orthogonal quantum state, which is ket 1, lives at the south pole. And all the quantum states, the general quantum state, as you all know, for a qubit is A ket 0 plus B ket 1. All of these quantum states, remember, it has to be normalized. All of these quantum states live on the surface of this sphere. Ket 0 lives on it, ket 1 lives on it, everything lives on this sphere. And A and B can be complex numbers. So we start off our assignment of the states to the Bloch sphere by looking at the computational states ket 0 and ket 1, put them on the north and the south pole. So this is our equatorial plane. This thing is our equatorial plane. Now there has to be kind of an axis that's pointing towards you. It's a 3D object, but I can't draw it on 2D sphere. So this is really pointing towards you. There is this point. So this is like an x-axis. This is like an x-axis. This is like a y-axis. And this is like the z-axis. Remember, it's not the Cartesian x, y or z axis. I'm just calling it x, y or z for clarity. Now, the state ket 0 lives on the z axis at the very top. Ket 1 also lives on the z axis, but at the very bottom. There is a state that lives here on the x axis inside the equatorial plane. That's an equal superposition of ket 0 and ket 1. So this point here, let's call this point A. A corresponds, the point A on the Bloch sphere corresponds to 1 over under root 2 equal superposition of 0 and 1. All right. It kind of makes sense because this x-axis is in between ket 0 and ket 1. This point here on the y-axis also has an equal superposition of 0 and 1, but with a different phase factor. So let's call this point B. The point B corresponds to 1 over under root 2 ket 0 plus iota ket 1. All right. Now, if I go to the back of the Bloch sphere, the dark side of the moon, which you can't see at the very back, this is also a point on the equatorial plane, and it is also an equal superposition of 0 and v. It must have equal amounts. The phases could be different, but equal amounts of 0 and v, because that point is equidistant from ket 0 and ket 1. So this point C is 1 over under root 2 ket 0 minus ket 1. Okay. And this point here on the minus y axis, this point D is 1 over under root 2 ket 0 minus iota ket 1. All right. So these are the points on the equatorial plane, but the equatorial plane has an infinite number of points, not just A, B, C and D. Suppose I take a point P here, a point P, and this point P makes an angle phi with the x-axis. Now this rings in some bells. This is like the polar coordinates. I hope you've all seen polar coordinates. So this is an angle phi. Can you, with this kind of prescription, come up with a formulation for what the point P represents? What is P? Yes, please.
Sir, 1 over under root 2 ket 0 plus E I iota theta ket 1
Plus E
I iota theta
phi.
ket 1.
Shabash.
Sir, say it.
Are we only looking at the surface of the Bloch sphere?
We're only looking at the surface of the Bloch sphere. These quantum states are only on the surface, they're not inside. We're looking at special kind of quantum states that only live on the surface, not inside. Those are different kinds of states. We're not dealing with them in a first course on modern physics. So all the points on the equatorial plane can be assigned a quantum state. Yes, please.
What would cos phi ket 0 plus a high sin phi ket 1 work?
No, it won't work. Now let's look, but it's not just the equatorial plane. You have the entire expanse of the northern hemisphere and the entire expanse of the southern hemisphere at your disposal. So how do you define arbitrary points? So you have a point here, Q, right? So now let me redraw this Bloch sphere because it's gonna get a little bit of messy. So this is my Bloch sphere. Here's a point P on the surface. There's a point P. This point P makes an angle theta with the North Pole. Suppose this angle is theta. That's very much in line with your nomenclature that you generally deal with when you study polar diagrams. So theta is the angle. So you come down from the North Pole. At the North Pole, theta is 0. And you slightly keep on coming down from the North Pole. At the equatorial, your theta is 90 degrees. Halfway in between is 45 degrees. theta could be anything. At the south pole, theta is pi, right? So this theta, generally called the angle of co-latitude, is measured from the north pole. So this angle is theta, but this point P could be pointing towards you, so it could be, so suppose this is my north pole, move down by angle theta, but this theta will have different values of phi. So this point P could be anything on this circle, on this little circle. So I need to define its phi as well. Theta alone is not sufficient because all of these points here on this little circle will have the same value of theta. It's like having a sphere and chopping off its head. All the points on the chopped off part will have the same value of theta but different values of phi. So what I need to do, I also need to define its phi. So I need a polar angle and I need an azimuthal angle. Polar angle tells me how down do I come from the north pole, and the azimuthal angle tells me how much do I need to turn around, right? So I need this kind of, so I make a projection onto the equatorial plane, connect this projection with the origin. This angle is phi. Now any point onside this Bloch sphere can be characterized by theta and phi. That's all I need if I'm just living on the surface of the sphere. The radius is 1. So theta and phi will tell me everything there is to be told about this quantum state. All right. Now could you please tell me what this point represents? So can you write a general quantum state in terms of theta and phi which corresponds to this point P? What we've done here, this point P, what we've done here, we've kind of parameterized all the points on the equatorial plane. The general form is this. Now I need to put theta into the picture. I give you 2 or 3 minutes to think about this and come up with a general expression for a quantum state that lives on the Bloch sphere, and the results must match that ket 0 lives here, ket 1 lives here, and this is the equatorial plane, and so on. What's the general quantum state in terms of theta and phi? Please answer my question first. Go. You can't say?
P की हेल्प से ट्राई करा था तो
Shabash, very good. Anyone else? सवाल जो कर लिया जवाब? वो थीटा इज विद रिस्पेक्ट टू कैट 0.
तो कैट 0
हाँ, वो जो प्रिस्क्रिप्शन है वो सब पे मैप होनी चाहिए. कैट 0 पे भी, कैट 1 पे भी. Is there a second student in the class who's done this? Yes, please. No. Most of the students would kind of do it the way you do, but yes, please. Can you speak up? Exactly. So our new P, this point is a quantum state. Its proper description is cosine theta by 2 ket 0 plus ei phi sine theta by 2 ket 1. On the for example, when theta is 0, this thing is 0. So you have ket 0. When theta is 180 degrees, theta is 180 degrees, this is 0. This is ket 1 with the global phase factor, doesn't matter. When theta is 90 degrees, you're on the equatorial plane. Right? When you're on the equatorial plane, theta is 90 degrees, cosine of 45 is 1 over under root 2 ket 0 plus ei phi 1 over under root 2 ket 1. So you have the proper kind of prescription. Anywhere in between, you just apply this formula. It's not theta here, by the way, it's theta by 2. If you put theta, your kind of these fiducial references, these reference points will not align with your definition. Yes, please.
सर हमने अभी बात की कि अगर सर्कल के सेपरेट पॉइंट्स पे जो ऑपोजिट हैं, 2 पॉइंट्स होंगे तो दे हैव टू बी ऑर्थोगोनल. तो हाउ इज दिस ऑर्थोगोनल टू द इक्वेशन अबाउट?
This thing?
जी.
This thing? They're not orthogonal. So this is a point on the equatorial plane. This is some arbitrary point. Let's call it Q. Some other point Q. The state that is orthogonal to this state will really be on the opposite side here. And you will find that state by changing theta to pi by pi minus theta and phi to phi plus 180 degrees. Yes, please. ये कैसे किया है? हर चीज़ डिराइव नहीं होती ज़िंदगी में. ये दरअसल what I have in front of me is a Bloch sphere, and I know that the north pole is ket 0, the south pole is ket 1. Additional information I have is that on equatorial plane I have ket 0 plus ket 1 with under root 2. So I need to put in some factors of theta and phi so that all of this makes sense and it maps to the points that I'm very comfortable with. And you will see that this works. So let's look at this quantum state, right? So this is my psi. On the equatorial plane, I put theta is 90 degrees, right? So on the equatorial plane, what is this angle of co-latitude? What is this angle on the equatorial plane? How much do I need to come down to reach the equator? 90 degrees. So if I put theta equals 90 degrees here, the quantum state turns out as cosine of pi by 4 ket 0 plus ei phi sine of pi by 4 ket 1. Now this is 1 over under root 2 and so is this. So I get 1 over under root 2 ket 0 plus ei phi ket 1. And these are the points on the equatorial plane. So it maps to all the points on the equatorial plane. It's all making sense. It's internally consistent, this definition. So it applies to any point on the Bloch sphere. Now let's look at this problem of a proton inside a magnetic field in terms of the Bloch picture. What's happening here is the quantum state is evolving with time, and this is the time dependent quantum state. Now we would like to represent this time evolution on a Bloch sphere. Sorry? Exactly. The quantum state is going to trace a circle on the equatorial plane. So let's kind of draw this. Our Bloch sphere my initial quantum state initially is here. It's ket 0 plus ket 1 over under root 2. My initial quantum state, which is at time t equals 0, is 1 over under root 2 ket 0 plus ket 1. Now what is my Hamiltonian? what direction is my Hamiltonian in? Does it have a z operator, x operator, or y operator? Z operator, because the magnetic field is in the z direction. So my Hamiltonian, at the back of my mind, I just remember that my Hamiltonian has a kind of, it's pointing upwards, the field is pointing upwards. Now this is my initial quantum state, and with time, the quantum state is precisely what I've written over here. Is this time dependent? Does this change with time? At time t equals 0, does it give me the initial state that I've written over there? Yes. But what happens with time? So my time dependent quantum state, which is a solution to the time dependent Schrodinger equation, is 1 over under root 2 ket 0 plus ket 1 with a phase factor. So I pick up a phase factor here, which is ei omega t. Omega t also turns out to be a nice phase factor because omega is a frequency and t is time. So you multiply the two together, it becomes a dimensionless constant. It has to be dimensionless. Now if you look at this quantum state, this white quantum state which changes with time, it's going to trace a circle on the equatorial plane. This quantum state here is exactly the same quantum state as I have over here, just that the phase factor is now time dependent. So what does this quantum state look like in time? It's going to go around in a circle. So with time, its phase is going to change. At some point in time, it's going to reach this point, and then it's going to be this particular quantum state. Some later time, it's going to go back to the Bloch sphere, back end of the Bloch sphere. At that point in time, its state is going to be, there's going to be a minus sign here, right? And so on. So I start off like this, my quantum state is like this, my Hamiltonian is perpendicular to my initial state in a sense. I start off like this, ket 0 plus ket 1. With time, I go around in an equatorial plane under the action of that Hamiltonian. This is how my quantum state is changing in time. And it's going around with the frequency. Now what is that frequency, omega? It's gamma b. It depends upon the magnetic field. Stronger field, slower field. So this spin is now precessing inside the magnetic field. This motion of the quantum state of the spin is called precession. And the precessional frequency omega is gamma b. Stronger the magnetic field, higher the frequency. This frequency, by the way, is also called the Larmor frequency. Larmor frequency. Now different objects. Now I'm going to give you a homework problem. What's the Larmor frequency of a proton? You have all the values for gamma. You'll find out that this frequency in a magnetic field of 1 Tesla is 42 megahertz. Because omega equals b. So if I were to apply a field of 1 Tesla, which is the unit of magnetic field, and insert the value of the gyromagnetic ratio for the proton, this frequency, of course, is in radian per second, but if I convert it to hertz, it's going to be 42 megahertz. So you put a proton inside a magnetic field, and if the initial state is in the right orientation, which is perpendicular to the magnetic field, this proton is going to precess with the frequency, which is the Larmor frequency. Now what I could do is if I were to kind of, what I could do now is I can discuss two things. The first thing I could discuss, this is my quantum state. What I would like to do is I can view this precession in another fashion. And this is very important because this ties up with the latter half of this class today. Now I've written a unitary operator. Given a Hamiltonian, I've written a unitary operator. This were my Hamiltonian, which is defined on the basis of the physical problem at hand, a spin inside a magnetic field whose direction is specified. From that Hamiltonian, I've constructed this unitary operator which acts on the initial state, yielding the quantum state with time, the general scheme of things. Now if you look at the Bloch picture, this looks like a rotation. It's really looking like a rotation. Now when you rotate something, how do you define a rotation? What do you need to specify a rotation? You need an axis. First thing you need to specify is you need an axis of rotation. About what axis are you rotating? And what's the second thing you need? The speed or the amount of rotation or the speed, right? Angle, or that's also the same as the amount of rotation. Torque is a mechanical concept, but you need two things. Okay, let's keep it simple. You need an axis of rotation and you need the amount of rotation. So in this case, if you view this quantum state's precession as a rotation, there's an axis of rotation. What's the axis of rotation here? Exactly. The Hamiltonian defines the axis of rotation. The Hamiltonian this defines the axis of rotation. And it also defines the amount of rotation, because this part defines the axis and this part defines the amount of rotation together with time. Omega t defines the amount of rotation. So the Hamiltonian tells you the amount of rotation and the axis of rotation. So if I were to analyze this, if I were to analyze the unitary operator, let me write down the unitary operator. U equals E minus iota omega t z over 2, right? So this is my unitary operator, isn't it? This is my unitary operator. Got it? That's so far so good. Now when I write a unitary operator in this form in terms of the Pauli operators, when I divide the Pauli operator with 2, that bit defines the axis of rotation. As a general rule, I'm giving you a rule of thumb, and it works. And it can be mathematically proven. So this z over 2 represents the axis of rotation, which is the z axis. Omega t represents the amount of rotation in time t, and that's what's happening in this case. The amount of rotation in time t indeed is omega t. So in time t, the quantum state precesses by an amount omega t. and the z axis defines the axis of rotation. All right. So if I were to generalize this case, e raised to power minus I, any angle, let's call this angle beta, any angle beta, into z over 2. This is a unitary operator. Every unitary operator represents a rotation. Now this is a rotation about the z axis on the Bloch sphere, and by how much? By beta. All right. So if I had my Bloch sphere and my initial quantum state were ket 0 plus ket 1, and this were my unitary operator, which means my Hamiltonian were along z. What's going to happen after time t? This quantum state here is going to rotate through an angle. How much is that angle? Beta. So after time t, this quantum state is going to change through an angle beta. Now if my initial quantum state were over here, let's see what's going to happen. On the Bloch sphere, my quantum state is ket 0. My initial quantum state is ket 0. My Hamiltonian is also along the z axis. So my axis of rotation and my state, they are both parallel. Will the state rotate? No. If the state is parallel to the axis, it's not going to change with time, because any point on the axis of rotation doesn't change. That's how we define an axis of rotation. So all of this is making sense. We started off from the time dependent Schrodinger equation. We kind of looked at the evolution of states, then we introduced the Bloch picture, and then we introduced this kind of notion of precession. If I were to define e raised to power minus iota beta x over 2, what would this mean? It's a rotation about the x axis. Keep in mind this factor of 2. This factor of 2 has to be kept below the Pauli operator. Anything else that remains is the amount of rotation. This corresponds to an rotation by beta about the y-axis. For example, if my initial quantum state were ket 0, suppose my initial quantum state were ket 0, and I were to apply a magnetic field along the x direction. So I apply a magnetic field along the x direction for some time t. Now the Hamiltonian for this process h is going to be h bar omega. Omega is now gamma times b, but now b although is in the x direction, multiplied by x over 2. This is my Hamiltonian. Correct? In complete correspondence with this Hamiltonian. Now I applied a magnetic field along the x direction, and my initial quantum state is along the z direction. It's ket 0. Will this state change with time? Yes. What's going to happen? It's going to come round. So this is my axis of rotation, this is my state. All right? Now this state is going to change, and how is it going to change? This state is going to come down like this, right? So this is my field, this is my Hamiltonian, this is my quantum state, the axis is this, and this is my state. So I rotate the state about this axis, right? I move towards the equatorial plane, I move towards the superposition, and I can stop wherever I like. I can stop as long as my field is active. I'll stop there. When my field shuts off, my precession shuts off. So this is also precession, but now this precession is about the x-axis. If my initial quantum state were parallel to this, nothing would happen. So in this case, my quantum state is going to come down after some time, and the amount of rotation is omega t. With some time, it's going to come down, and this kind of coming down is the amount of rotation is omega t. And I can also prove all of this. I can prove all of this mathematically as well. For example, if this were my Hamiltonian, my unitary operator is going to look like E minus iota h bar omega t over 2 h bar x. So this h bar just goes away, and I'm left with a scenario very similar to this, exactly the same thing, but with a z replaced by an x. So this becomes cosine omega t by 2 identity minus iota sine omega t by 2 x. Now if I were to write this in matrix form, let's see what it looks like. Cosine omega t by 2, cosine omega t by 2, and for the off diagonal terms, my x is defined like this. This is my definition for x. So I just multiply this with this factor, left with minus iota sine omega t by 2 minus iota sine omega t by 2. Now this is my unitary operator. This can act on any initial quantum state. Now after a 10-minute break, I'm going to describe how logic gates can be built out of these magnetic fields in the physical sense. So let's take a 10-minute break. All right. Something really interesting here. Quick recap. Excuse me. The first example, field along Z our Hamiltonian is h bar omega over 2 field along Z. So I have a Z pointing magnetic field, I have a proton inside this magnetic field, I draw the Bloch sphere, my field is along Z, this is my field, this is my Hamiltonian. Suppose my initial state were here. Now this Hamiltonian tells me I need to do a rotation about the z axis. So this is my state, it's on the x axis, this is my axis rotation, it's going to rotate in the equatorial plane. Its z is not going to change now, but it's going to rotate in a circle, in the equatorial circle. This is how my quantum state, which started off as ket 0 plus ket 1 over under root 2, this is where I started off with. And with time, I've already seen through this notion of the Bloch sphere as well as through the explicit expression for the time dependent quantum wave function that this state is going to be ket 0 plus ei omega t ket 1 over under root 2. This is how my state is going to change with time. So if my omega t is 0, I am here. If my omega t is pi by 2, if this is pi by 2, I come here. If my omega t is pi, I go to the back. So I keep on circling around. the equatorial plane with a particular frequency which is omega. The time period is 2 pi over omega. It's a periodic rotation. Now the point is, how does this relate to nuclear magnetic resonance? So if I were to place, say, a detector suppose I have a detector, some kind of detector that detects spins, and I place that detector on the x-axis. All right, let's suppose for a minute, I'll tell you physically how to do this. I want to find out the probability that this detector clicks. So this is my time dependent quantum state. I want to project it onto an observable state. So I'm now measuring in a basis. Whenever I want to do a measurement, I measure in a basis. So here I put my observation along the x direction, which means I'm measuring in the ket 0 plus ket 1 over under root 2 ket 0 minus ket 1 over under root 2 basis. Now, since you're familiar with photons, so just to give you an example of polarization of photons, when we deal with photons, I have a photon coming in and I pass this through an analyzer. I pass this through an analyzer which has two output ports. Correct? So one is the output channel ket 0, the other is the output channel ket 1. This is my initial quantum state psi, my input quantum state. So the probability that this detector clicks, what's that probability? That's not half, it's come on, it's ket psi is something arbitrary. It's the overlap of ket psi with ket 0 modulus square, right? This is the probability that the upper detector clicks here. Got it? That's how you compute probabilities. And the probability that the other detector clicks is psi overlap with ket 1 modulus square. Correct? That's how you measure quantum states. Now the basis of measurement here is ket 0 and ket 1. But you can measure in any basis, and we've seen examples of this. For example, you could have your photon polarization coming in, and you could have a device, a beam splitter, that outputs two channels. This is ket D channel, or 0 plus 1, and this is the anti-diagonal channel, right? So there's a detector over here and the detector over here. So how do you find the probability that this detector clicks? How do you do that? So you find the overlap of this quantum state with this output state, right? So how you do that? You just take psi overlap with, let's call this ket D modulus square, correct? So you can, now you're measuring in another basis. When we discussed non-locality, we also looked at other bases. So you can measure in any basis you like. All right? You got this? Now the point is, what I'm doing here in this experiment, I try to measure the quantum state along this x-axis. So I need to find the projection of this quantum state on my choice of basis, on the axis about which I would like to measure. So I put a detector here. Let's call this an x detector, px. The probability that this detector clicks is x. So I'm calling it an x detector because really it's pointing on the x axis of the Bloch sphere. So if I were to calculate this probability here, the probability that my x detector clicks Now, is this going to be a function of time? Is this probability going to change with time? Because my quantum state is changing with time. So, what is my quantum state? Psi t. Psi t. And I want to overlap this quantum state with the kind of state upon which I am going to measure it. And that state is kind of the diagonal state, or the spin pointing along the x direction. And that state is ket 0 plus ket 1 over under root 2. Right? So, this is my ket, this is my bra, and I take the modulus square of this. That's my probability that a detector pointing along x is going to register some signal. All right? Quantum mechanics is kind of really consistent. It's a coherent picture. It applies to all different kinds of physical scenarios. Now, let's compute this. So, my quantum state is function of time under the Hamiltonian. Still I have my z pointing magnetic field switched on. It's the field is precessing, the quantum state is precessing. This is my quantum state at any time. So, 1 over under root 2 ket 0 plus e I omega t. Now, this is a function of time. The basis is not a function of time. The measurement axis is not a function. That's fixed. My detector, its location is fixed. So, I project this onto 1 over under root 2 ket 0 plus ket 1 modulus square. So, if I were to compute this, this is 1/2. Take the square 1 by 4. This gets out of this bracket. Now, ket 0's overlap with this is non-zero, it's 1. Plus, this gives me e I omega t. Now, I need to take the modulus square of this part. Correct? 1 by 4. 1 plus complex conjugate multiplied with the scalar itself. This is how you find out the. So, this turns out to be 1 by 4, 1 plus e I omega t plus e minus I omega t. This is 1 by 4, 2 plus 2 cosine omega t. Now, this is 1 plus cosine omega t over 2, which I think is cosine square omega t over 2. So, if I really had some kind of detector that could measure this spin, it's the intensity, so the hypothetical intensity that I could get from this spin is going to be an oscillatory function with time. So, if I were to plot this with time, the probability that my detector X clicks is going to be cosine square function, sorry. So, this is the probability that I project onto ket 0 plus ket 1. If I were to project onto the orthogonal state at the back, I will just get 1 minus this probability, and you can work it out. If I were to project it onto ket 0 minus ket 1, I will get a sine square omega t over 2 as my answer. So, I will get the kind of the opposite thing. This is projection along minus x. Now, what is really magnetic resonance? Here we have a single spin, one spin inside a magnetic field. Now it's very hard to do experiments with a single spin, with just one spin. It's really hard to do that, because first of all, it's exorbitantly hard to isolate a single spin, a single proton. There are experiments that can do that, but it's very hard. So in a real NMR experiment, like the NMR that you have just about 20 meters from here, there is a hot soup of liquid. There's a solution, an aqueous solution, suppose of an organic molecule which has many protons in it. And you place that inside a magnetic field, and then these spins precess in the equatorial plane, and you have, for the detector, you have a coil. Here you place a coil. It's like a solenoid. A solenoid pointing in the x direction, whose axis is along the x direction. Correct? Now, you know that these tiny spins, they are like magnets. They are magnets. So when a magnet has a magnetic field, when a magnetic field cuts a coil, what's going to happen? An EMF is going to be produced. That's going to produce a current. And the frequency of that current is going to be equal to the Lama frequency, the precessional frequency. And that is then recorded in a computer. And this Fourier transform is taken, and you get a spectrum. This is how an NMR spectrum works really. You can also have a coil along the y-axis. So if in this experiment, this is a homework problem by the way, if you were to measure along this axis, so you have a Hamiltonian that induces an axis of rotation. The amount of rotation is defined by the time. How long does it take and how fast does that rotation take place? And when you have that, you can also have detectors to detect your magnetic field. Now if I were to kind of build upon this concept a bit further, any questions by the way? This is kind of cute what I've described. Now suppose my magnetic field is along the x direction. So my Hamiltonian is h bar omega over 2 x. My initial quantum state, initial at time t equals 0 is ket z. I want to apply a magnetic field along the y direction, sorry. A field along the y direction. My Bloch picture. My quantum state is ket z to begin with. My Hamiltonian is along the y-axis. So with this Hamiltonian, what is my unitary operator? What is my rotation operator? E minus I omega t y by 2, right? Got it? Fine. And I can also use my theorem to expand this, and I can write the matrix for this. I can write the matrix for this. Homework problem, write the matrix for this. Now with this operator, now you have an axis of rotation. What I do is, with time, this is really important and really nice. I have this magnetic field pointing along the y direction. It's 0. At time t equals 0, I switch it on. And I keep it on for some time, capital T. And then I switch it off. My quantum state were ket 0. Now at this point in time, my quantum state is going to see the impact of a magnetic field. It's going to feel the magnetic field. Now because it's going to rotate. Now what is its, the quantum state is going to change with time. So within this period, when the field is switched on, its state is going to change. Can you predict what the quantum state is going to be after time capital T? First of all, let's look at it geometrically. This is my axis of rotation and this is my quantum state. It's nice to anthropomorphize quantum physics. So this is your kind of axis of rotation. This is your quantum state, right? You begin with. Now, how is this state going to change under the impact of this axis of rotation? Isko nahi chedna. You don't want to change this. This is your fixed axis. Now, how is this quantum? So, I rotate that quantum state about this axis. Exactly. So, it's going to come down towards the equatorial plane and it's going to keep on coming down until you switch off the field. Suppose, okay, start, and I say stop, you switch off the field. Stop. Capital time T has elapsed. Now, this state, if you were to draw this quantum state, can you, okay, that's fine. Can you draw, excuse me, would you be able to draw this quantum state here? How this state, can you visualize this on the Bloch picture? I want you to visualize this evolution on the Bloch sphere. So this is your state. How is it coming down? Exactly. Shabash. So this quantum state is going to come down gradually with a frequency omega. It depends upon the strength of the magnetic field. It's going to come down towards the equatorial plane. On this, if I were to draw a big circle here, a meridional circle, this quantum state is going to come down on this and it's going to stop somewhere, right? It's going to, it might come all the way down to the equatorial plane. It might overshoot and go into the southern hemisphere. It depends upon this time. And it also depends upon the strength of the field, because if the field is stronger, that frequency is faster. So in short time it can move longer amounts of angles. So it depends upon the product of omega and T. So by the way, mathematically, what is this state going to look like after time capital T? Badjo. What is this state after time T? So let's look at the Bloch sphere. This is the general form of a quantum state on the Bloch sphere. Can you use that general form? What's the polar angle of the final state? Omega t is the polar angle of the final state, isn't it? Because the amount of rotation is omega t. The amount of rotation is omega t. That factor of 2 has been clubbed together with the Pauli matrix. This tells you the amount of rotation. The amount of rotation is just the angle theta. That's omega t. So at the end of time t, at this point, the state is going to be cosine of, now this angle theta, the angle by which this state has come down is omega t, capital T. So this is cosine of omega capital T by 2 ket 0. Now what is phi for this big circle? It's 0 because it's kind of on the 0 GMT, 0 longitude, right? There's no tilt there's no azimuthal angle. It's coming down right on the big circle. So phi is 0. So I don't care about phi. and I'm left with sine omega capital T over 2 ket 0. Cute. Now if this omega t is pi by 2, 90 degrees, then I'm left with the state on the equatorial plane. I have created a superposition. Oh, nice point. Not really, but close to it. It's not really. Very good question, by the way. I'll explain that. So if this omega t is 90, pi by 2, I put pi by 2 here, this becomes pi by 4, and I'm left with cosine of 45 degrees. I end up at the equatorial plane. So if my omega t is pi by 2, my final state, which is this point here. So I time my pulse, this magnetic field and its strength, so that I start off here, I end up here. So my final state is 1 over under root 2 ket 0 plus 1. If my time is twice of this, I start here and I end up at the south pole, ket 1. And I can go all around the circle. This kind of pulse, proper timing such that omega t equals pi by 2 is called a 90-degree pulse, because it takes a state and brings it down to the equatorial plane, creates a superposition. And this is an example how you physically implement close to a pseudo Hadamard. It's not really a Hadamard gate, I'll explain why, but it does a 90-degree rotation. I could do a pi rotation as well. Question for you. I can take a question before that. Yes, please.
Sir, does this operation define a phase gate in any way?
No, it doesn't. That's a Z gate. This is an X gate or a Y gate. So this is an example of a 90-degree pulse. All quantum computing architectures use 90-degree pulses. They create superpositions. If I would like to ask a question. Now, without looking at the mathematics, you can look at the Bloch sphere and answer my question. Field along the y-axis. Initial state is a superposition 0 plus 1. And I apply a y pulse for this much time, for omega t equals pi by 2. Where will this state go? It will go down. So this is my axis of rotation. Anthropomorphize yourself. This is my axis of rotation. This is the state. 90-degree rotation will bring you down to ket 1. Another 90-degree rotation will bring you back. Another 90-degree rotation will bring you all the way. A 2 pi rotation all the way back, but you'll check that with the minus sign. But that doesn't matter. With a minus sign. Homework problem, 2 pi rotation about the y-axis, you incur a minus sign. But that doesn't matter because it's a global phase. And that's why it's a spin half particle, because you actually need 2 rotations, 4 pi rotations to bring it exactly back with the same sign. That's why it's called a spin half particle. Yeah, that's why it's a fermion. Now the question I would like to ask, with this knowledge, how do I apply a NOT gate? How do I apply a NOT gate? Now you have some kind of semblance of a physical system. You have magnetic fields, spins, and you can start building quantum computers. This is what they practically look like. Now, with this kind of analysis, how do I build a NOT gate with spins? A quantum NOT gate. How can I build a quantum NOT gate that takes ket 0 to ket 1 and ket 1 to ket 0? What kind of rotation do I need? What axis of rotation do I need, and what's the amount of rotation do I need?
Y-axis.
Y-axis, okay. And a pi rotation. Doesn't matter, I mean, 0 goes here, 1. So is this correct? a pi rotation about the y-axis, because what that does, this is my rotation axis. I start off with 0, my axis, or this is my axis rotation. I start off here, I do a pi rotation, I slowly go to the equatorial plane, and then I move back, move to the southern hemisphere, stop here. That's a pi rotation. So I started off at ket 0 and I end up at ket 1. If I started off at ket 1 and I do a pi rotation, I'll go all the way back to the northern hemisphere. I'll end up at ket. So, well, so how do I write this in matrix form? Simply E minus I, what's the amount of rotation? Pi. And the axis of rotation? Y. So I put y over 2. Sorry. Y over 2. Now the problem is that this is not a NOT gate. नेगेटिव का कोई फर्क नहीं पड़ता, वो बात नहीं है. It's not a NOT gate. The reason, what is your NOT gate? What is your ideal NOT gate? Your matrix must give something proportional to this. Homework problem, find out the matrix for this with the theorem that we've just employed. The problem is, now let's look at this scenario here. If I start off, if I have a 180 degree rotation, a pi rotation about the y-axis, and I started off with ket 0 plus ket 1. Now I need to kind of ask you and spot check here. Can you tell me where that state is going to land after 180 degree rotation? I start off here at ket 0 plus 1. This is my axis of rotation. Where do I end after a 180 degree rotation? I go all the way back. So what is that state? Ket 0 minus ket 1. So with this rotation, let's call this u pi. Let's call this u pi about the y-axis. I'm just giving it a name. A rotation through pi about the y-axis. So if I have this rotation about the y-axis and I apply this to ket 0, it works. It gives me ket 1. I don't care about the global phase here. There might be some global phase as well, but I don't care about it. If this state acts on ket 1, I indeed get ket 0, as is evident in this Bloch geometry. However, if this state acts on ket 0 plus ket 1, I get a state that is proportional to, as my friend has just elaborated, ket 0 minus ket 1 over under root 2. Does this then qualify as a NOT gate?
Can you rotate about ket 0 plus ket 1?
अभी आप थोड़ा आगे चल रहे हो. So does this qualify as a NOT gate? What if we feed in this state into a NOT gate? Does it change? It should not change. It shouldn't change at all. But here it's changing because now there is a phase between ket 0 and ket 1. Therefore, naively this might appear, a pi rotation about this axis might appear as a NOT gate, but it's not really a NOT gate. It's kind of a pseudo NOT gate. It only works with special initial states which are ket 0. It does not work with arbitrary states. The unitary operators act on any states. So it must be a NOT gate for this input state, and as my friend there has just mentioned, a better rotation would be a 180 degree rotation about the x-axis. If I were to do a rotation about the x-axis and a pi rotation about the x-axis, so this were to become my axis of rotation, I would still achieve the effect of ket 0 going to ket 1, ket 1 going to ket 0, ket 0 plus 1 will remain there because it's now parallel to the axis of rotation. So now my quantum NOT gate can be implemented by turning on a magnetic field along the x direction for a precise amount of time. How do I build a Hadamard gate? Every quantum gate on a qubit, single qubit, is a rotation. Every qubit is a rotation. How do I build a Hadamard gate? Yes, please. No, that's the state. How do you build an operator? You do how big a rotation do you need?
90.
About why? About what?
About y.
About any three of the axes we choose, but it should be.
Okay, so the proposal is you do a 90-degree rotation about y. Let's see. Bloch sphere, y-axis, and you want a 90-degree rotation about the y-axis. That's what you want. That's what you propose. So you're proposing this E minus I, amount of rotation is 90 about the y-axis. So this is your prescription. You can write the matrix for this using the theorem, another homework problem. Now let's look at this from a geometrical perspective. If I start off with ket 0, after this 90-degree rotation, where do I end? So I end up at the equator, the equal superposition state. So I do end up here at ket 0 plus ket 1. And that's what a Hadamard gate does. That's what a Hadamard gate really does. So what a Hadamard gate does is it takes ket 0, Hadamard gate, and it converts this into 0 plus 1. So this qualifies as a Hadamard gate. It's a legitimate Hadamard gate, but we also have to look at the other input state. The other input state is, if I were to feed in with ket 1, a Hadamard gate produces 1 over under root 2, 0 minus 1. Does this operation achieve that? 90-degree rotation about the y-axis, you starting off with ket 1, you end up at the back side, which is this state. Viola. बिल्कुल ठीक, लेकिन problem एक. What if I apply a Hadamard gate on this state? Ideally, if I were to apply a Hadamard gate on this state, what should I get? I should get ket 0. But if I were to start off with this state and apply a 90-degree rotation about the y-axis, do I go back? No, I don't. I keep on advancing forward and I move on to ket 1. Therefore, a 90-degree rotation about the y-axis is only a kind of, it's a pseudo Hadamard, it's not a real Hadamard gate because it doesn't work for all inputs. It only works for specific inputs. So can you come up with a recipe? I need to define an axis of rotation and an amount of rotation on the Bloch sphere that defines a real Hadamard gate. 1 minute to think about this. Any ideas? Yes, please.
Sir, maybe if you have ket 0 going up like this and you have superposition going like this, you take an axis which goes between them.
Beautiful. And how big a rotation do you need? Oh, beautiful. So you really need a kind of tilted axis. So if I were to draw my equatorial plane again, sorry, my Bloch sphere again, z-axis, x-axis. I draw an axis in the xz plane, 45 degrees. This is my axis of rotation. So my axis of rotation is now neither along z, neither along x, but halfway in between. I keep it halfway in way between and do a 180-degree rotation about this axis. So if I were to start off here, I will move in a cone, come here. I will do it again, I will move back in that cone and come here. So it's really a 180-degree rotation about a tilted axis. And I think I should give this as a homework problem. So the rotation is E minus I pi x plus z under root 2, which is cosine 45 and sine 45 with a factor of 2. This is my matrix. And I can use the theorem and find out what this looks like. So please do this as a challenging homework problem. Inshallah, see you on Thursday.